remember before he joined Purdue. His research is in the broad area of computational fluid dynamics, in particular in the development of physically consistent models, high-order numerical methods, and efficient algorithms, as well as their applications. More recently, his research is focused on the modeling and the computation of multi-phase flows, neural network-based numerical methods, and algorithms and their applications to computational mathematics and the mechanics problems. So today, Stephen is going to give us a talk entitled Local Extreme Learning Machines, a neural network-based spectral element-like methods for solving PDEs. So please join me in welcoming Stephen.
Hi, George.
Hi, Steve. Hi, Steve.
How are you doing? So can I first try to share my screen to see whether it works?
Yeah. Already, I make you a
okay.
co-host, so you may share your screen.
All right. Can you see the screen?
Yep.
Okay. Great. Thanks, George, for the invitation, and also and thank you for the opportunity to be here, to be back, to speak to the Crunch group. Actually, I have a picture of the group when I was here. I joined the group in August 2001, a few weeks before the 9/11, and then I think this picture on the top left was taken the winter of that year, and this picture was taken in the summer of 2003. And between 2003 and 2004, I learned gradient descent from George, and I did a gradient descent on my weight. And this is a picture of me the afterwards in 2005. But anyway, I'm very glad to be back to speak to the new generation of the Crunch people. So in this talk, I will introduce the neural network-based methods for solving partial differential equations. I call this method local extreme learning machines, or local ELM. The characteristics demonstrated by this method are reminiscent of those of the traditional high-order methods, such as the spectral or spectral element-like methods. So that's why I call this method a spectral element-like method. So here's the outline of this talk. So first we'll review some of the ideas of the neural networks, and then we'll discuss how to use neural networks to solve partial differential equations. And then we'll concentrate on local extreme learning machines and discuss how to use this method to solve linear PDEs and also nonlinear PDEs. Afterwards, I will use several numerical examples to demonstrate some of the properties of this method, as well as the characteristics. So the neural networks, especially deep learning, has achieved great success in the past few years. So we all know the AlphaGo from several years ago, and more recently, the AlphaFold for protein folding in the image processing, text processing, etc. Now, I'm working on the scientific computing. So I'm interested in the following questions. That is, how will these techniques impact scientific computing? And do these methods provide a competitive technique for numerical simulations? So that's the questions I'm very interested in. So in this talk, we'll focus on neural networks for scientific computing, mainly for solving partial differential equations. The scientific computing has its own characteristics, which are not necessarily emphasized in the other fields like image processing, the other areas. So for example, accuracy and computational cost are very important properties of a computational algorithms. So we'll focus on these aspects. I will try to answer the following question, at least partially. That is, can neural networks provide a competitive method for scientific computing, especially in computational PDEs? So, can we develop a competitive method for computational PDEs? So that's the question I will try to answer. There are several acronyms. The ELM stands for extreme learning machines. Local ELM, the local extreme learning machines, etc. So here we'll consider the simplest neural networks, feed-forward neural networks. So this figure shows a sketch of such a network, feed-forward neural network. So we have the input layer, we have the output layer, and we have a number of hidden layers. Now, from layer to layer, the logic represents a affine transform as well as a function composition based on some activation function. So the neural network basically represents a parameterized function, which is constructed by repeated function compositions and affine transforms. The parameters of the neural network are basically that's the coefficients of the affine transforms. Now, another point is that for solving PDEs, usually on the output layer, we do not impose any activation function. So the output layer is basically linear. Now, the neural networks have the universal approximation property, which basically says that the functions encountered in the real world can be approximated by the neural networks to any desired degree of accuracy. So the neural networks are universal approximators. Now, how do we use neural networks to solve PDEs? So if you're given PDE boundary conditions, initial conditions, for example, and then in order to solve the problem, we first use the neural network to represent this function. Remember, the function is a parameterized function. So the theta are the parameters here. So we'll try to find the parameter theta such that this function, parameterized function, will satisfy the equation, satisfy the boundary condition, and satisfy the initial conditions. Now, exactly satisfying these conditions and in the equation is very hard. So we'll try to relax the requirement a little bit. So we will try to find the parameter theta such that the errors of the equation in some norm, the errors of the boundary condition in some norm, or the errors of the initial condition in some norm will be minimized. So that's basically the PDE solution problem will be transformed into a minimization problem, and then we can use the optimizer to find the parameters. So that's the idea for solving PDEs. There are, of course, many variants. So for example, we can use the discrete norms, or we can use the weak forms of the equation, etc. In the past few years, a number of prominent methods have appeared in the literature. The PIN was pioneered by this group, here, the crunch group, and the deep Glerkin method, deep Rees method, etc. There are many related methods. Now, there are several drawbacks with these existing DM-based PDE solvers. The accuracy of these methods seems to be quite limited. A survey of the literature indicates that the error levels, if you look at these papers in the literature, the errors of these methods seems always to be on the level 10 to the -3 or maybe 10 to the -4. If you when you increase the training epochs, it's very hard. It's very hard to make a significant improvement to this error level. Now, the accuracy of this level is not exactly satisfactory for scientific computing. Related to the accuracy, there seems to be a general lack of convergence with a certain convergence rate. So, for example, if you increase the number of layers or the number of nodes per layer or the number of training data points, it's very hard, to see a consistent improvement to the simulation results. Another drawback is that the computational cost is extremely high. This network is very, takes a very long time to train. So let me use an example to illustrate this point. So this is a 1D Helmholtz equation, computed using PIN DGM with the atom trained by the atom, as well as the classical finite element method. Here, this table shows the maximum error, L infinity, L2, the number of epochs, as well as the training time. Now, with the PIN DGM, the error level is around 10 to the -3 or 10 to the -4. The training time is around, several hundred seconds, 500, 400 seconds. Now, with the classical FEM, with the 25,000 elements, you can achieve error level around 10 to the 8. And the computation time is around, around 0 point something the seconds. So it seems that the current DM-based methods are not quite competitive, compared for solving PDEs, compared with the traditional numerical methods. So we want to ask the following question. So can we devise a neural network-based method for solving PDEs that has a sense of convergence with respect to the simulation parameters, and as well as computationally competitive compared with the traditional methods? The answer to this turns out to be positive. Partially, more or less. And in this talk, I will introduce a neural network-based method that, in a sense, overcomes these drawbacks. So this method has a clear sense of convergence. Its numerical errors decrease exponentially. I mean, for the smooth solutions, decrease exponentially with respect to the number of training data points and the number of training parameters. Is computationally competitive. Its accuracy and the network training time, the computational cost, is competitive compared with the traditional methods. It is actually on par with the classical finite element method. And for larger problem sizes, it outperforms the FEM. So I will show that a little bit later. So I call this method local extreme learning machines, or local ELM. This method is a combination of three ideas: the random way neural networks, or especially extreme learning machines, domain decomposition, and the local neural networks. Another important point of this method is that the training of the neural network is by the linear or nonlinear least squares method. It's not by the back propagation or gradient descent type algorithms. This is very important. So the training is by a linear or nonlinear least squares method, not by the gradient descent. Extreme learning machine was proposed by Huang et al. Around 2006 for single hidden layer feed-forward neural networks for linear problems for the classification regression. And the ELM absorbs some ideas from the random weight neural networks. So the random weight neural networks, the basic philosophy is this: since training the entire neural network is extremely hard and costly, so perhaps if we assign a subset of the network coefficients to random values and fix them, we can probably make the optimization, the resulting optimization simpler, ideally linear, without severely sacrificing the achievable approximation capacity. So that's the idea, that's the philosophy of the randomized neural networks. So ELM absorbs some of the ideas of the random way neural networks. It has two ideas. The first one is that it'll preset or assign the network weights in all the hidden layers. All the hidden layer coefficients will be assigned to random values and fixed. And then the neural network will be trained by linear least squares method because they are considering the linear problems. So it'll be trained by linear least squares method. So that's the two ideas, the main ideas there.
Steve, how many of the weights? What percentage of the weight is prefixed?
What's that?
What is the percentage of the weights that is prefixed?
So all the coefficients in all the hidden layers, they are fixed. Only the output layer coefficients are trainable.
Okay.
So that's the idea.
That's definitely not so you don't get the best basis.
No, it's not necessarily the best base, but they're random bases. Yes.
Okay.
So so how do we use the local EM to represent the functions? Now here's the idea. We first partition the domain into subdomains, and then on the subdomain boundaries, we impose the CK continuity conditions. So K here is related to the PDE order. So if we have a say PDE of the mth order, then we'll usually impose the CM-1 continuity conditions on the subdomain boundaries. Now the function on each subdomain is represented by local feed-forward neural network, and all the hidden layer coefficients will be assigned to random values and fixed. Only the output layer coefficients are trainable. And then for solving linear PDEs, we are going to train the neural network by a linear least squares method. And for nonlinear PDEs, we are going to train the network by a nonlinear least squares method. So that's the idea. That's the philosophy or the basic idea. Now, based on this description, on each subdomain, we have this expansion relation. The left-hand side is the output of the neural network. Right-hand side, the VI is the output field output fields of the last hidden layer of the neural network. Beta J are the training parameters or the output layer coefficients. So basically on each subdomain, based on the philosophy, the function is expanded in terms of the set of random basis functions. So that's the I think that's the basic idea. That's the main idea. It's similar to the in some ways is in a similar spirit to the spectral element, but here is a set of random nonlinear basis functions. So that's the key here. So how do we use the local ELM for solving PDEs? So let me use a linear PDE as an example. So consider here a second order boundary value problem with the linear PDE boundary conditions. So we first use the local ELM to represent these functions, the domain, etc. And after that, we generate the collocation points on each subdomain, and on the subdomain boundaries. And then we enforce the PDE on the collocation points of each subdomain, enforce the boundary conditions on the collocation points of the domain boundaries, and enforce the CK continuity conditions on the subdomain boundaries. Now, this will give us a set of linear algebraic equations. Now, these set of linear algebraic equations about the training parameters or expansion coefficients of the output layer. Now, this system is not squared. Usually, it's not squared. So we use the linear least squares method to solve this system for the values of the training parameters. So that's the basic idea.
Steve, can I ask you a question before,
before
you transition into the PDE part? So the premise of this is that you get some sort of special basis from randomly just choosing the hidden layer parameters. Can you explain what is the desirable feature of that random basis? Because of course you could just use a spectral basis or whatever finite element basis you want here, right? So this must give you something special.
Right. So my feeling is that so given these random bases, the least squares sort of if you're given a set of random bases and then the linear least squares sort of extracts the best the best information from that set of bases.
But how could it be best since it's suboptimal? For example, I can foresee cases where you can have a linear dependence of the basis because you flip the coin. So you have singular metrics.
Yeah, some of the bases maybe, they are random. So maybe linearly, some of them maybe linear dependent or maybe close to linearly dependent.
Yeah.
But the least squares, when you solve these, the least squares sort of take that into account. It sort of extracts the best information, the best solution from that set of bases.
Right. And another point, Steve, is that this is not learning. If you look at the information bottleneck theory, learning is two parts. You're doing the fitting part. But if you don't have, as Naftali Billy showed, that if you don't have random weights, then you cannot visit other parts of the landscape, of the lost landscape, and therefore you cannot learn anything new. You can do a good job in training the data and solve this equation, but you don't learn anything. So it shouldn't be called learning. It's a solution to PDEs.
George. So since the problem is over-parameterized, and the solution, if there's a best solution or close to best solution, that solution is not likely to be unique. If you use the gradient descent to get some solution, that's maybe one set of solution, but there may be other set of solutions that may be better than that or maybe close to that. There may be other solutions. So these kinds.
I'm not talking about the uniqueness of the solution. No. I'm not talking about the uniqueness of the solution. I'm talking about the randomization of the weights and the fact that the weights fluctuate in a stochastic gradient descent, the parameterized network, allow you to go through what is called what Chibili is calling a diffusion period. So after the sort of advection period. The whole he explained the whole thing as the Fokker-Planck equation. So the training period is like the advection period, and then in the Fokker-Planck, and then the diffusion period is the long period where basically the gradients of the weights in the stochastic gradient descent become order 1 from 0. The mean gradient weight is 0 because you converge. But so you are sort of saying here, after I converge, I finish. But that's the point where you start learning. So that's why it cannot be called learning what you're doing. You can solve the equations.
George, I think what is learning? So eventually, at the end of your training process, you'll have a set of values for the coefficients in the hidden layers and the output layers. Now, if you use the say gradient descent step, I mean in that way, eventually you get a set of values for the hidden layer coefficients as well as the output layer coefficients. Now here, this is so what I'm saying that this is another set of values for those coefficients. The previous value, those are random values, but they are fixed. And then the output layer, those coefficients, I choose those set of values. So I use these as the representation of the field or function. So if you use the other way to get another set of values, that's another representation of the field or the solution. So I mean, whether these two fields or two solutions, which one is better? I mean, that we can compare or we can test it, right?
Please go on.
All right, yeah. Okay, but that's the right. That's the basically the technique here. So let me continue here. So if you carry out this process, so basically that's the PDE, and then you get these system boundary conditions. So here we have second order in the PDE. So we impose C0, C1 conditions. So this is a linear algebra system for the beta J. That's basically the training parameters or expansion coefficients. Now the differential operators, there are a number of differential operators involved here. They can be computed based on the auto differentiation of the neural network. Now this is not a square linear system, so we use the linear least squares method to find the value of the training parameters or the expansion coefficients or the output layer coefficients to get the value. Now, if the PDE is time independent and want to find the solution for the time variable from 0 to t, the capital T. Now, if capital T is small, then we can treat for these time independent PDE, we can treat the time variable in the same way as the spatial variable. So you can get collocation points from the spatial temporal domain. Similarly, you can get a linear algebra system, use the linear least squares method to get the values of the training parameters. And then, so this is very similar. Now, if the capital T is large, that's if you want to do the long time simulations, if you train the neural network on the entire domain, it becomes very hard, to train in the sense that the solution may contain very pronounced errors in the solution, especially at later time instance. So in this case, we use the block time marching, the idea. So basically, marching block by block. So we partition the temporal dimension into a number of windows. We call it time blocks, and then compute each time block individually and successively. On each time block, the problem is basically we solve that using the method on the previous slide. So we take the collocation points in the spatial temporal domain, etc. And then after the solution, one time block is obtained, we use the solution at the last time instant as the initial condition for the next time block. So basically, that's exactly the marching, block by block. So you find that with the moderate time block size, the neural network becomes much easier and faster to train. You get more accurate results. So that's for the time-independent PDEs. Now, what if the PDE is nonlinear? So in this case, the procedure is similar. So we can represent the solution by the locELM representation, enforce the equations, boundary conditions, continuity conditions on the collocation points. the thing is the algebraic system you obtain is non-linear, it becomes non-linear. In this case, we use a non-linear least squares method to solve the system to find the values of the training parameters. So again, the differential operators can be computed by auto differentiation. It's similar in a similar way. Now, if the PD, if the nonlinear PD is time dependent, it's similar. For long time dynamic simulations, we can use the block time margin, and on each time block, we use the nonlinear least squares to solve the system. To get the values for the training parameters. So in this case, for the nonlinear PDs, especially for long time dynamic simulations, even when the temporal dimension, the t becomes moderately large, the block time margin becomes critical. So without it, it's very hard to get the accurate solution or to get the correct solution. So that's basically that's the idea. There are of course many details, but these are the main ideas for the method.
But Steve, I still I'm confused about all this background information, because this is exactly CPIN with a cheap version of CPIN without backprop.
The one thing, George, is different is that on the different subdomains. So let me put it here. On different subdomains, because these local neural networks, they are physically not connected, but actually they are logically coupled because of the CK continuity conditions. So we need to train the neural network, all together. That's in a coupled way.
CPIN and XPIN do the same thing. You have different neural networks on different subdomains.
Right. Yeah. In that sense, there are similarities. Yes.
No, it's exactly the same thing, except the no backprop, which you have a good reason not to use backprop, but you're losing the learning, as I told you, I think. But I don't.
Okay. Yeah. In terms of the one thing, George, I think is different. I think you in I think 2020 there are the CK continuity condition. I'm not sure. I don't think you impose the CK continuity there on different.
Ameya is here. He can tell you that he imposes the CPIN, not the XPIN. There are two versions. And then I see a note from Nat that I know that his least square method, where he breaks it up into two parts. And I think that's that method. Nat, you're somewhere in between, right? Because you do the one part is least square, and with the convex part, the other one is the.
We do the same thing. So we solve a least squares problem for the linear layers, and then we go back and do a step of gradient descent to get the hidden layers. So if you just skip the gradient descent step, it would give you the same thing. But the gradient descent step is what gives you the adaptivity and tailors
of the basis. Yeah. That's what I'm saying. You are somewhere in between, and between what we're doing and what Steve is doing.
Right. I recall there are similarities, I think, but this one actually right. Yeah. There are similarities. I agree with you. Yes.
You're familiar with the work that Nat put in
yes. I think I read their paper on arXiv. I'm not sure. I think later probably they have published version. I didn't read the published version.
Yeah. Okay.
I'll follow up with you and we can talk offline.
Okay. Yeah.
It'd be good to catch up.
Right. I think over there right. You use the least squares to solve them, then you use the gradient descent to for the other coefficients probably. Yeah. Right. Yeah.
Please go on.
Okay.
Sorry for the interruption.
But that's the basic idea. That's the overall. I mean, there are details, but that's the overall idea here. Now, for the implementation, the neural network here implement TensorFlow, Keras, etc. for the linear for the linear least squares method, this is implemented using the LayPy routines, which is available from the SciPy. The nonlinear least square is also from the implementation of the from SciPy, which basically is a Gauss-Newton method plus a trusted region. Now the the linear least squares with the TensorFlow with the default fast option is very bad. You know, the accuracy is very poor. Another important the point with the nonlinear least square is that in order to do the nonlinear least square, you need to incorporate some routines for perturbation in order to prevent the solution from being trapped to the local minimum solution. So that's there are some important points. Now, so this method has several properties. I mean, it's very hard to get this from the theory, but I will use several numerical examples to demonstrate this. The first one is the exponential convergence. That's the numerical errors decrease exponentially with respect to the degrees of freedom. That is the number of training parameters, the number of training data points. Its performance, here performance, I mean the accuracy and the computational cost or the network training time is competitive compared with the classical finite element method. For smaller problem sizes, the finite element method is a little better. For the larger problem sizes, the local ELM outperforms the FEM. Compared with the high order FEM, is also competitive to a certain degree. But in general, you know, as of the writing of the paper, it is in general not as efficient as the high order FEM. And also, I will compare with the PIN DGM. It seems like in terms of the accuracy and the cost, it seems to be much better than PIN and DGM. I will show that with several numerical examples. So let me next use some examples to demonstrate some of the properties. The first one is the 1D Helmholtz equation. So here this figure shows the maximum error and the RMS error as a function of the collocation points per subdomain. So here there are two subdomains with the single hidden layer, the neural network. So here you see a exponential convergence, and then afterwards there's a level off. There's the level off, the saturation there. So these are the errors with respect to the number of training parameters per subdomain. We see a close to exponential convergence here, and then there's a saturation. So this is a computer using, again, two subdomains with two hidden layers in the neural network. So that's the maximum errors. And as a function of the collocation points, we see exponential convergence and saturation. And here, that's the network training time. As a function of the collocation points, it grows near there's a near linear growth in the computational cost. So this is a comparison between the local ELM and the PIN and the DGM. So here that's the function distribution, the error distribution. Basically the DGM PIN is on the level around 10 to the negative 4th. And here we can achieve around 10 to the negative 8. So this table shows the maximum error, RMS error, as well as the training time. So the PIN DGM, that's around the level 10 to the negative 3 or negative 4. And with the time is around 700 or 1000 seconds. And the local ELM, we can achieve 10 to the negative 9. The training time is around 1 second.
Steve, what's the width of the linear layer?
What is that?
What is the width of the final linear layer for this?
I think I don't have the exact number here. Let me see the table is here. I think the number of collocation points per subdomain is 100. The number of training parameters per subdomain 100. So that corresponds to this case, 1.1. So that's this case. So there are basically 100 uniform grid points. So here I in these computations, these are the collocation point. These are the uniform grid points.
I think that asks about the number of neurons, right? In the
right. The number of neurons 100. That's 100. The M here. M is the number of training parameters. That's the last hidden layer, 100.
So I think the fair comparison to make here is with a spectral element with a 100-degree polynomial.
100-degree polynomial. I'm not exactly sure, but because here the activation function is tanh, so I'm not sure, the degree, whether how to relate that to the polynomial. If you use a polynomial basis, how to relate that to the polynomials. There might be, you can suggest that, because this is basically that's the number of expansion coefficients. So in some sense, there's a relation, but I'm not sure how to relate that to the polynomial degree. So that's one thing I'm not quite sure.
It's the dimension of the finite element space.
The space is the 100. That's the dimension of the random, the basis, the number of random bases.
And if there's value in using a random basis, right? Spectral elements are designed. A spectral basis is designed to be optimal for smooth functions. Right. So if there's some value in using a random basis, that's the comparison that will show for what class of solutions this is a better choice of basis for. You know what I mean?
Yeah, it might. So my understanding is that the tanh or the others, nonlinear basis, the activation function, that's basically is a series. So you get a series with a polynomial, the basis. If you use 100, say I use the polynomial space of degree 100 or something like that. And with the tanh is a series. So the polynomial in terms of the polynomial degree, it contains infinite, these polynomial degrees. You use different series solutions as or series to do the expansions. That's the one thing I'm not quite sure, how to relay these. Say I have 100 bases, random basis functions. How do I relay that to the polynomial order or the polynomial degree? That's something I'm not quite sure. But it is a legitimate question. Yeah, I've been thinking about that.
Can we see the solution? Can we see the exact solution for this?
Yeah, it's here.
Right. What is F here? Oh, this is the exact solution. Okay, so
yeah. That's the
I can tell you how many if you use 1, 2, 3, 4, 5, 6, 7, 7 spectral elements, and you use about 10 order polynomial, about 100 degrees of freedom of spectral element, you get the solution very, very accurately, the machine accuracy.
Mm-hmm. Yeah.
Very easy. Just count the numbers, basically the wave numbers, and then everything.
Yeah.
Okay.
Yeah, that's something I'm not quite sure. There, if you look at that, there's the philosophy in terms of the spirit. There are similarities to the spectral element, the idea, but I'm not sure how to relate that. Relay these two. So here, basically we have a number of tanh. These series of polynomial series or power series. Use that as there are some random parameters there. Use that as the basis for the expansion. So here, this is a comparison of the local ElementLike with the FEM. That's the linear elements, classical the finite element. So here, this table shows the number of elements. Number of subdomains for the ElementLike, local ElementLike. Q is the number of collocation points per subdomain, and M is the number of the training parameters per subdomain. Max error, RMS error. The FEM, that's the computation time. The local EM, that's the training time. And then if you compare the highlighted case, they are similar in terms of the time and accuracy. But when we increase that, the local EM is better than the FEM. Now, this is the 2D Poisson equation. Here, that's the errors as a function of co-location points. Here we have two subdomains, etc. And then that's the training time as a function of the co-location points. There's a near linear growth. That's the classical FEM, the second order convergence, computing the same problem. And that's so here we vary the mesh size. And the computation time versus the elements per direction, that's the computation time. Now, if I plot these two together, so here we plot the maximum error in the domain as a function of the FEM computation time and as a function of the local ELM, the training time. So here, that's the curve we have. So the triangle is the FEM. The circle, that's that's local ELM. So here, notice that with the local ELM, we increase the number of collocation points per direction. With the FEM, we have to increase the mesh size per direction. And there's a crossover point. On the left side, the problem size is smaller mesh, smaller set of collocation points. Right-hand side, the problem is larger. So here we see that the crossover on the left-hand side, the FEM is better. So which means that in the sense that with the same computation cost, the FEM can achieve a smaller error, or to achieve the same error, the time with the FEM is smaller. With a larger problem size, the local ELM is better. So that's in a similar sense. So basically, with the larger problem size, the local EM can outperform the classical FEM. Now, this is a comparison with the local EM with the high order FEM. So here, high order FEM is because the FEM here is implemented using the Phoenix, the library. We want to find a Python, we don't have the Jacobi, the libraries here. So here we use the Phoenix. The Phoenix, they're the Lagrange elements. The triangular elements, basically you put a number of points and then you can generate the high order, the Lagrange elements, the basis. So here, that's compared here. This is the Lagrange elements of degree 3. That's degree 4. So degree 4 here, that's the largest problem size we can run. So here again, this is the increasing mesh size. So the degree element order is fixed, but we are increasing the mesh size. Here, that's the largest we can run on a Mac computer here. So these two are the local ELM, the result. That's the maximum error versus the computation time or the training time. So here, in this case, we can see a crossover. So here, local ELM is a little better, but overall, compared with the high order FEM, at this point, in general, it seems like local EM is still competitive to some degree, but in general, it's not as efficient as the high order FEM. At this point, that's as of December 2020, last year when the manuscript was written. So here, that's the diffusion equation, in 1D plus time, and that's the analytic solution. So here, that's the error in the error distribution in the spatial temporal domain with the local ELM on the error level 10 to the negative 8 or something. This one is the error versus collocation points. We see the exponential convergence. So here, that's the local EM with the 10 time blocks when computing this. That's the in time. And this one is comparison with the classical FEM. So here with the FEM, when the number of elements increases, the delta T also decreases proportionately. So here when you see the error, you can see the second order convergence. So they are almost exactly four times. The wall time, maximum error, RMS error. This one is the local ELM. And if you compare the highlighted case, so the computation time is similar, but here the error is smaller, much smaller than that, and similar to the other cases. So basically, local EM performs better than the FEM. Now this one is comparison between the local EM with the DGM and the PINM. So that's the error distribution. Notice that here the time here is only to 1. When comparing these with larger, it would be very hard for the DGM and the PINM. So here that's the error level, error distribution, and that's the error distribution for the local ELM. The error level already, the order magnitude is different. And this table shows the maximum error in the domain, in the RMS error, training epochs, training
So,
time.
hello. Hi, it's
Yes.
Amir from Brown.
Yeah.
Do you think that it's fair to compare with the XPin rather than pins here? Because both are, or XPin or CPin, because both are domain decomposition based methods, because you are always showing the training time for pin here, where you are using actually a single network.
Single network. That's I don't think that's I don't think that will make much difference. So if I use a single domain here, it's again the error is comparable to this level. So it's not that's not the reason here.
It's in terms of computational time, actually, not in terms of error.
Computation time. So we can I don't have the XPin. I'm not sure here. But this is the comparison with the pin. Yes, so that's you know, overall you get the you're trying to get to decrease that loss. I'm not quite sure how this will compare with the XPin there.
Okay.
As you mentioned.
Thanks.
So if the XPin is much faster, I think there might be a difference in terms of the accuracy and the computational cost here. But these values, these are from the pin, from the atom and LBFGS. So that's basically for the diffusion equation. So this one is the advection equation. The advection equation, again, in the X domain, we have the periodic boundary conditions. In time, you know, that's this solution. But one thing this solution, notice that this initial condition does not exact. For one thing, this does not. There's the partial U partial X. The derivative there is not periodic. So basically, it's not smooth. So that's why this will limit the accuracy you can achieve. But here again, we see the exponential convergence with the collocation points, the training parameters, for these. Now this one I want to show is that for the long time simulations. So this one is the computational domain in time is to 100. So here we use 100 time blocks, and within each time block there are the 8 subdomains. So that's the solution distribution. In the spatial temporal domain, that's the error distribution. And this one is the time signal at the midpoint of the domain comparison with the exact solution. So here, you know, the basically overlap. The error is I also have the error signal, but it's not here. So what this means is that with the method and the block time merging, really you can do the long time dynamic simulations. So that's the point here. Now this is a nonlinear problem, nonlinear Helmholtz equation. That's 1D here. Again, you see the exponential convergence. Here that's with respect to the collocation points, and this one is a comparison. Is a comparison with the PINN. Here the error level is around 10 to the -3. I mean, the accuracy level in the training time is quite different. I have this is a comparison with the FEM. So FEM, the number of elements, the error level, the wall time, local ELM. If you compare these two, the highlighted cases, they are similar. But when you increase the problem size, the local EM becomes better than the FEM. That's the Burger's equation, the viscous Burger's equation. That's the analytic solution used to test the problem. And that's a comparison between the local EM and the FEM. So here, with the number of elements increases, the delta T decreases. Again, you can see the second order convergence for the FEM. And the local ELM, if you look at the highlighted case, their error level, computation time is similar. But when you increase the problem size, the local EM outperforms the FEM. that's a comparison between the local ELM and the DGM, the error distribution. So notice that here in the comparison here, we use a very small, the temporal domain to 0.25. With the larger, that really it becomes very hard with in terms of the errors. The error level is really quite different, and that's the maximum error, training time, etc. Their error level and the computation time is really quite different. I think that's basically what I have here. The local ELM, it seems like it has quite high accuracy. The exponential convergence, I think, is very attractive, and the computational cost is relatively low. The training time is compared with the classical FEM is computationally competitive, and with larger problem sizes, it outperforms the FEM. With the high order FEM, the other point of the writing of that manuscript, it is not as efficient as the high order FEM yet, but we are catching up. It's actually right now with improved implementation, we can outperform for the high order FEM. It seems like this is superior than the DM based or the PDE solvers. So the content of this talk is mainly based on this paper, which appear in the CMME. There's another the recent manuscript. So here that's with improved ELM. We show that basically the ELM can with improvement can outperform the high order FEM, and also compare with the classical FEM becomes much better than that. So I will probably stop here and see if there's any question. Thank you.
Steve, I have to go to another meeting, but did you actually do any inverse problems?
No.
Did you avoid them on purpose or?
No, because that's the first. I'm thinking about the inverse, the problems there, but I haven't done that yet.
Because as I said, the way I see this is basically X-pin without backprop. So you replace, that's totally X-pin without backprop. You just replace, you just do one random initialization and replace the solver, the backprop and so on. But I mean, if the purpose is to solve PDEs, there are spectral elements, and you cannot beat the spectral elements since you cannot beat finite elements and that. But the purpose is for learning, in other words, transfer learning. So that type of things. So you have to consider that. I don't know if you have. When we develop pins, it was not like to replace spectral elements. It's to solve problems that you cannot, where there's noisy data, where there is, where you learn, where you do transfer learning. But learning, as I said, look up learning, what learning means. Learning doesn't mean fitting. Otherwise, it's fitting.
No, this George. So when I compare all of these errors, it's actually when I train these, say on 20 by 20 the collocation points. So after that, I generate a 100 by 100 grid. I evaluate the network, compute the error there, compare that with the exact.
No, that's the same network. Learning means, you know what generalization is? I'm talking about generalization. Yeah. Learning means generalization.
Yeah. Right.
So I don't know how, if you cannot visit, when you, I invite you to look at that paper by information bottleneck by Naftali Chiftili, and then you will see what I mean. I can talk to you offline because I have another.
Yeah, okay.
Thank you very much for coming, and you can keep going with the discussion.
Yeah, I think I'm done here, unless there are other questions.
Steve, I have one last suggestion before I have to run too.
Yeah.
For extreme learning machines, the place where they've worked really well is for image problems that are very high dimensional. And in that space, there is something that you get out of this random basis. It's that neural networks can embrace the curse of dimensionality, and you can't make a tensor product spectral element basis. It's too expensive. It blows up exponentially. So one place that might be, so that you're not trying to like compete with spectral elements, a place that might be fruitful would be to look at high dimensional PDEs, where you can do spectral elements, and now all of a sudden, like, this basis becomes valuable in that sense.
Actually, I think actually the question I'm very interested in is exactly this. That I want to know whether this really can outcompete the spectral element. So that's one thing, I'm interested in. So essentially, there's an indication. I have the manuscript here is posted a couple of weeks ago, is here. So let me show a comparison here. That's exactly, this is for the Poisson problem. So here, this is again, that's Lagrange elements. So here, degree 5. That's degree 5, you see the convergence for the high order FEM. That's the classical second order. The computation time, second order, this is the degree 5. And then that's the local ELM, improved ELM. And that's the error with respect to collocation points, the network training time with the collocation points. If I plot them together, that's what I have. This is with the second order. Compare with that. It's far, this one there, this is different than the paper in the published version. So this is with the high order FEM. This is the H refinement. That's the P refinement. So what do we have here? That's the maximum error. Also have the RMS error, similar trend. With respect to the computation time, that's the degree 3, 4, 5, 6. There's 7 approaching somewhere there. So what you have here is that, again, with the problem size increases, the ELM actually outperforms the high order FEM. With the smaller problem size, they are comparable. They're close, but the high order FEM is a little better.
That comes down to how you compare the P and the spectral element basis
here. So what I have here, but I can generate a trend here. So this is if I fix a mesh and then I increase the FEM, the polynomial, the element order. This one is I increase the collocation points, the ELM. So this is what you get. So different points. This one, that's the different degrees or the element orders. So what this shows is that they are very close now. They're close even for the same problem. I think they can compete with the high order FEM. Here, these bases, I want to point out that it's not exactly the Jacobi polynomial. So that's the Lagrange polynomials. I'm not sure how different these two are. I think they're probably in some sense maybe comparable. But here, what this indicates is that the method here is, in some sense, can close to the high order FEM. That's what I'm saying.
Yeah, makes sense. I'm happy to talk offline if you're interested in talking more.
Yeah.
Is there any questions for Steve? Well, I actually have one question for you, Steve. So I think it's a trivial question, but did you try to use a different initialization to see how much different would the result be if you use a different initialization of parameters, like
you
the
mean
weights and biases?
or what?
Or your local ELM?
Different initialization, what do we mean?
For different initialization for your ELM model.
Yes, I did. The here I tried a different the seed values. You know,
Yes.
the initialization, that's because that's done in Keras. The Keras, there's a generate the random values. So with the different seed values, yes, I do have that.
Okay, so
So similar. The characteristic is similar, but their values, the exact error values are not the same, but the level is comparable. The error level.
Yep. Is there any questions for Steve? If not, let's thank our speaker again. Thank you, Steve. That's a very, very wonderful talk.
All right, thank you.
Yeah, that's the end of this week's seminar. Everybody take care. Bye.
Okay, bye.